just as a reminder, what is a ring? Okay. So R plus. Let me emphasize that it is one of the things we could do in describing a ring is we could say R star star prime. Indicate that there are two binary operations, and we don't know exactly what those binary operations are. They may be defined to be something quite different from ordinary addition and ordinary multiplication. But rings are always written this way, right? And the two operations are written as plus and times, even if they're not plus or times in the usual sense. It simply means there are two distinct binary operations. How do you distinguish between the two? Well, whatever one of these is plus forms an abelian group. Which means, under addition, or the operation that's called addition, it satisfies all of these conditions. Multiplication is only defined to be, required to be associative. Always need associativity. So this is sort of maximal structure for plus, minimal structure for multiplication in order to have a ring. And so this is required to be associative, and that's all. But there is one other condition. Since there are two operations, how do they interact with one another? And those are the distributive laws. There's the left distributive law. All of this says, by the way, that multiplication distributes over addition. So A times the quantity B plus C is A times B plus A times C. And that's the right distributive law. Since multiplication is not commutative, I can't just turn this around and say the left distributive law works too. Multiplication may or may not be commutative. It's not required to be. In which case, when I talk about the left distributive law, I also have to talk about the right distributive law. And this is A times C plus B times C. Examples of rings that we know. The reals. Usual addition, usual multiplication form a ring. What else?
Integers.
The integers. C, under addition and multiplication, form a ring. What else? Okay, good.
What did she say?
She said complex numbers. This is addition of complex numbers and multiplication of complex numbers. I'll give you a little bit more about this example later. These are all three rings. If we go back, what I'd like to do is build this up as close to a field as we can. And if I use R to stand for a ring under addition and multiplication, now I want to go towards a field, which is our maximum structure for a set of two binary operations. R plus is an abelian group. Notice, 0 in R can't have a multiplicative inverse. So, what I want to do is throw 0 out of R and consider, is it possible that R without 0 forms also an abelian group?
Are you always assuming that you're throwing 0 out?
Yes.
Okay.
Because 0 times anything is 0. And along with the distributive laws. This is an important thing for you to know because I would be very surprised if in your version of the test that you take, you won't have a question about fields. What are fields? Fields are rings, i.e. sets with two binary operations, such that under addition, we forms an abelian group. That's true for all rings. But under multiplication, except for 0, it also forms an abelian group. And the distributive laws hold, which again is true in any ring. So, when you go beyond just requiring multiplication to be associative, notice except for 0, we're requiring the existence of a multiplicative identity, that there exists an inverse for under multiplication for every element, and that multiplication commutes. All of these things must be true in order for this to be an abelian group.